Hey everybody, it's Professor Tomney, and I just wanted to give one more quick reminder at the end of the course here for the website at chemcomplete.com. So we do have our own website where we offer services such as one-on-one mentoring and tutoring, and you can also pick up guides here that I have developed. So there is a guide for the spectroscopy course, which is what you've been following along this whole time. If you click on Buy Guides, you will see that there's a couple of them here. I'm trying to release one every 1 to 2 months, but the Unknown Organic Structure Spectroscopy Guide is available for purchase. It's $15. It helps to support the channel, and it has dozens of pages with information. I've created appendices with tables to help you reference ppms, chemical shifts, IR vibrations, things like that. So if you have the affordability and the time, I really appreciate you coming over here to support the channel. And this will help when you go through the practice session that we are about to do, because you want to have your tables handy. Now, you by no means have to have this guide. You can go back through the other videos and look at what I'm saying, make some notes, but this just collects it all together, and it really helps to support the channel. So that's it for the shout out. We will go ahead and get started with our final part of the unknown spectroscopy lecture, where we are going to be solving a problem. Okay, so here we are, and this is the final part of the unknown spectroscopy course. So a while ago, actually several years ago, I posted a video like this on YouTube, and it was one of the most popular videos, which is what spawned my idea to do the whole course. And I will link that video in the playlist at the end of this. So you'll have this one, and then in case you haven't seen that original one, you can revisit that for additional practice. I will try to release some of these throughout the fall as we continue, but this is going to be the capstone for the current course right now. So let's take a look at what we have here. We've got an IR at the top. We have a mass spec with the formula here, so we will be doing degrees of unsaturation. We have a C13 along with the depth version, so that'll help us when we're looking at CH2s and quaternary carbons. And then we finally end with our Proton NMR. So those are the different portions that we've discussed in this course, and we're going to be bringing them all together and working on this now. So to start, we're going to start with degrees of unsaturation, just like we were taught in the course. So for degrees of unsaturation, we would be looking at the formula C8H10O2. Now we know that oxygens are going to be ignored, so we just really need to work with our carbons and hydrogens. All right, so we would use a 2 and then an 8, and after that it would be +2 minus, and then it's the number of hydrogens, 10. Now there are a couple other things thrown in there like the halogens and nitrogens. However, we do not have halogens or nitrogens in this formula, so we don't need to worry about that. And we're going to divide all of that by 2. So if we do that, then that comes out to 8 over 2, and 8 over 2 is going to reduce down to 4. So there are 4 degrees of unsaturation. Now, just seeing that, that's either a lot of double bonds or rings in a system, or there's very likely an aromatic compound. So whenever you see 4 or more degrees of unsaturation, you just mark down that you probably have an aromatic compound of some sort. It's not a guarantee based on just degrees of unsaturation by any means. However, it's usually a good guess. And we can always back this up by looking at the other spectroscopy. So even if you want to take a quick glance, you can see, oh, there's peaks in the carbon-13 in the 120 region, and then there are also peaks in the 7 to 8 region for the Proton NMR. So that's a solid formation. We know we're going to already be dealing with an aromatic compound. So then we move on. After the degrees of unsaturation, we're going to take a look at the mass spec briefly. So for the mass spec, we're going to look at the parent peak, which is at 138. That's the M+ peak. Okay. So if the M+ is at 138, that is the molecular weight associated with our compound, right? And then the other thing we can do is we can take a look at these identified peaks here. So what you do is you take 138 minus 121, okay? And you see what that equals. So that's going to equal 17. Now, 17 is a very common fragment. And if you have the guide or you've been following along and you understand common fragment patterns, you can see in the appendix for the mass spec in the guide that the 17 is a common fragment for OH. So there's potentially going to be an OH, and that is supported with the fact that we have an oxygen in our formula. So we probably have an alcohol of some sort, but we'll want to verify that through IR and NMR. Now, we can also do that by taking 138 minus 107, and again, if you have the guide and you look in the appendix, you'll see that the value for 31 is also a common fragment. It is OCH3. So there's potentially going to be an OCH3 if the degrees of unsaturation hold and we do have an aromatic, which we know we do. There's no more degrees of unsaturation left. So this could not be an ester because we wouldn't have a carbonyl that would require an additional degree of unsaturation. So we likely have some sort of an ether because of the OCH3 and some sort of an alcohol. But we want to verify it. So we're pretty much done with mass spec at this point. We're going to go on and verify through other spectroscopy. So you can see the pacing here and how much time I'm spending in each region. So I'm already nailing down some important parts. However, it's going to likely come down to looking at the IR and then really looking at the NMR is what's going to sort of tie everything together. So we continue along, and we're saying that we've probably got an aromatic ring of some sort, and there's an alcohol and also an ether. So maybe something where we've got an alcohol, and then somewhere, we're not sure where on the ring, so I'm just putting this generic line here, we've got an OCH3 group, right? There's some additional carbons that are required here because we have 8. So the ring would have 6 and that CH3 would be 7. So maybe there's a CH or a CH2 somewhere. Okay. And 107 right here, that's the base peak or the largest peak. So that represents the most stable ion. And if you look at just phenol, which is the aromatic with the OH, that comes out to 94, okay? But if you look at something with around a CH2, like this, which would be a very stable ion because of the resonance, if we put a plus there, that comes out to about 108. So perhaps we have some sort of form, maybe plus or minus a hydrogen, of this type of structure right here, okay? And again, I'm sort of arbitrarily placing the CH2 right now. It could be in any of those positions in terms of the resonance. Now, let's move on. So IR would be the next thing that we look at. We can clearly see that we have an alcohol confirmed by that broad rounded peak at 3,326 for the wave number. So the alcohol that was confirmed through the mass spec by the fragmentation pattern is also being further confirmed right here by the IR. Now we also see 1085 for a wave number. Now 1085 is really close to the region for a CO vibration, and that would confirm the ether type of activity because we said there might be an OCH3 that is associated with this based on the mass spec fragmentation pattern. So that is beneficial. We take a look at that. We can also confirm, as we stated earlier, we don't expect any carbonyls. So the region where we would expect carbonyls to be present, there is notably an absence of peaks. So we wouldn't expect any type of C double bond O. All right. And then finally, it's kind of hard to see, but if you look at this peak right here, okay, and I might zoom in and out a little bit as we go through this. So if we zoom in, that peak right there, okay, is just barely a hair over 3,000, okay? And it's kind of drowned out by this alcohol peak. However, we do know that we should have just north of the 3000 mark for wave number, we should start to see peaks that appear for aromatics. And so that would make sense as well. You also are going to find aromatic peaks right around here, even though those do not have a number or label on them right now. All right, so zooming back out here, that pretty much confirms what we want from the IR. So we're definitely working with an alcohol. We're almost certainly working with an ether at this point, and we have an aromatic ring. That's the basic structure we're going to work with. So now we head down to the carbon-13 and the proton NMR, and we're going to glean the most information that we can from those two. So let's start with the carbon-13, and then the proton will be the finale. So for the C13, all right, we're going to take a look. Let's look at the bottom, which is our basic proton decoupled. We'll take a look at that one first. So how many unique peaks do we see here minus the solvent peak? So this tiny one right here, that's our solvent peak. We're going to ignore that. So you've got 1, 2, 3. There's a tiny one down here that's 4, 5, 6. All right, and I will again zoom in so that we can see this a little bit better. So you can see 1, 2, 3. See this tiny one right here? That's 4. Okay, 5 and 6. So we have 6 unique carbons, and we have a total of 8 carbons in the structure. So there has to be some level of symmetry going on with the carbons when we're taking a look at this structure. And that makes sense with an aromatic, especially one if it was disubstituted, right? We would get some similarity between the carbons. So what we could start to suggest at this point is that perhaps we have an aromatic ring, and that aromatic ring is going to have a substitution pattern that is para, like this, right? With one group up here that we'll call X and another group down here that we'll call Y, because then we have these 2 carbons at the top that are going to be symmetrical, and then these 2 at the bottom that would be symmetrical. So that would give rise to a proper pattern like this. Okay, especially if you have the X and the Y, you have 2 different groups. Now if you have the same group, so if it was an X and then another X, like 2 chlorines or something of that nature, in that case you would only see 1 peak for all 4 of those. They would all be considered symmetrical when you're looking at the spectrum. So let's go ahead and zoom back out here. So what we're going to do now is we're going to kind of characterize these, and the depth will help with that. So the 3, 4, 5, and 6 are most definitely the aromatic carbons. And we know that because we have followed along with the guide and the ppm region matches up. And we also know there's no carbonyl. So even the 6 that's sort of further out here, that is not going to be a carbonyl because the structure will not allow for that based on many factors, the IR, the degrees of unsaturation, etc. So we have the aromatics, right? And then we have 2 peaks that are going to be hydrocarbons, but they will be hydrocarbons, most likely sp3 hydrocarbons, that are near electron withdrawing sources. Because look at how far downfield these are, right? We don't have anything in the 20, the 30 region. We're looking at about 49, maybe 48, and then another one that is coming in probably at like 75, okay? So if you take a look at the depth, 2 of the 4 peaks disappear. So peaks 6 and 4 are absent in the depth, and that means that those are quaternary. So the quaternary carbons are carbons that have no hydrogens attached to them, and a quaternary carbon in the case of the aromatic would be the sites of substitution. So where the carbons on the ring where we put the X and the Y group, those would be the 2 carbons that are disappearing in that case. Right? The other 2 represent the sets of symmetrical carbons. So that makes sense so far. So we then have most definitely a CH2 because of that invert. So remember we were talking about an OCH3 group and then maybe a CH2 or a CH. It looks like we've got a confirmed CH2 group here. And so this is most likely, okay, we're going to get further confirmation, but this is most likely going to be a CH3. All right, so this is shaping up. We know we've got an alcohol. We know we have an ether. and we know we've got an ethyl of some sort in the making here. So that's what we have put together from our carbon-13. You could probably come pretty close to solving this at this point, but we certainly want to cap this off with the proton NMR before we would make our final conclusion. So let's move down to that. And I think the ppm is slightly out of range here, so let me fix that for a second. Okay, that's better. So now we take a look at the proton NMR. Let's start down with the aromatics, because we know that we're going to have those, right? So we've got two signals down here. We actually have a third one. This says exchanges with D2O. So that will be our alcohol, because things that exchange with D2O usually involve hydrogen bonding. So they're oxygen-hydrogen bonds, nitrogen-hydrogen bonds, things of that nature. That integrates to one, and it's pretty far downfield, meaning there's a lot of hydrogen bonding activity and electronegativity. So that's likely going to be the alcohol. And then we have these two values right here around 6.7 and 7.2 approximately. They each integrate to 2, so that means we have 4 hydrogens on the aromatic ring. And that further confirms we have a di-substituted ring. We only have room for 4 hydrogens. Now, what's interesting, I'm going to zoom in here again. If you come in and you look, they zoom in this region, and they show you that these are doublets. Okay, it can be a little hard to see. I'm going to zoom in once more. Okay, right there. Those are doublets that we see there. All right, and if you have a doublet, it makes sense that when you're dealing with your ring structure, okay, if you have two commonalities, an X and a Y, two substituents there, and then you have this H and this H, these are going to show up as the same signal because of the symmetry. And so when you take a look at that, and they're going to show up as the same signal, you would expect it to integrate to 2, because there are 2 hydrogens associated with this, right? And then the neighbor, it's experiencing 1 signal from a single hydrogen down here, because these again would be symmetrical, so, right? So this experiences 1 hydrogen, this experiences the 1 hydrogen, so it's like a mirror right there. It's experiencing the same thing. So one neighbor, if you use the n+1 rule, would be 2, so we would expect a doublet. So this right here, this splitting pattern, most certainly confirms that we have a para-substituted ring of this nature. Right? Now I'm just going to delete that because we drew that up very close there. All right. So zooming back out now, so we can finish this. All right, so we have the ring. We know we have an OH, so let's take a look at what we've got here. Now, down here, these are the hydrocarbons. We indeed integrate to a 2, so this is likely the CH2 portion, and we have a CH3. All right, so what we want to consider at this point is starting to put the structure together and figuring out what we're going to have and if it makes sense. So we know we have an aromatic ring. All right, so we'll draw the aromatic ring out, and we also know that based on everything we've seen, the aromatic ring is going to be di-substituted in a para pattern. So when we do this, this is C6H4. So what we can do is we can start taking away from our molecular formula to see what's left, just to confirm. So it's C8H10O2. Now what I'll do is I'll subtract the alcohol, because we've confirmed that through IR and most certainly through the other specs that we have here. So you take that away, you're going to have C8H9O. Okay, and then you take away the aromatic ring, it would be C6. Now don't get confused, a lot of students will make a mistake and put H6 because that's benzene. It's H4 because these two sites at the top and the bottom are substituted. There's no hydrogen on them. So what that leaves us with is C2H5O. And so this is what we have to make our ether out of. All right? Now C2H5 is very common for ethyl. So we really have 2 possibilities. We could potentially have an OCH2CH3, Or we could have a CH2O CH3, and this would be attached to the ring, most likely. So when you take a look at this, okay, you should probably be able to figure this out at this point if you've been following the course along. But it's going to be the second option for several reasons. Number one, we did suggest that OCH3 would be a common fragment, and you can only get that from the second option, right? The OCH3. So that was via the mass spec. Then, if you continue looking, the HNMR is what really confirms it here. So in the Proton NMR, when you look at 2 and 3, these are singlets, okay? So in the top option here, if we were to look at the splitting pattern, not the integration, but the splitting pattern, you would have a quartet for the CH2, and you would have a triplet for the CH3. Whereas down here, you would have a singlet for the CH2 and a singlet for the CH3, and that's because the oxygen disrupts them. And in addition to that, in the top example, the CH3 would be much further upfield. It would be more shielded because it's not in direct contact with the oxygen. Whereas we look here, 3.5 and 4.5 are the approximate ppms. Those are way too high for the first option up here. So we are left with absolutely the CH2OCH3 as the ether. So what you would do at this point is assemble the rest of the molecule, and you would have OH, and then you would have CH2OCH3, and that is the final structure that you would work with. So hopefully you've been able to see methodically how we can work through these puzzles, and you get increasing bits of information that you collect as you go along, and they should always be supported by the original information you came up with. So we started with degrees of unsaturation, and every spec that we went through, we continued to build and snowball our evidence until we finally got to the Proton NMR, which was very rich in information using the integration numbers, the splitting patterns, and you tie it all together. That's a lot of support for your unknown structure, and that is how you solve these problems. So I hope that this course was useful to you. Be on the lookout for additional information. I do have a video coming up on how hydrogen bonding will affect chemical shift. It's pretty interesting. And as always, thank you for learning with us, taking the time to use our channel as your resource. And one more shout out just to the website. Go over to chemcomplete.com. Just check it out even if you're not going to buy the guide. But we always appreciate any support you give us. We love you guys, and we will see you for future courses. Good luck with all of your coursework this semester. Thanks a lot, guys.